Is that the original?
Yeah.
No. Wait, was he doing all? No.
You said no, you said are you sure?
All right. Here we go. So today we're going to talk about complex solutions to polynomial equations, which is going to, kind of involve talking about finding, basically doing what we've been doing, but then in addition to those rational zeros, right? Because that stuff we did not yesterday, 2 days ago. Stuff we did 2 days ago with the factors of the constant term over factors of the lead coefficient, right? That allows us to find rational zeros because those are fractions, right? Fractions are fine for the zeros. But then, of course, we know that there are other possible zeros, including real numbers and complex numbers, well, really complex numbers. So we're going to find out how to do that today. And like I said, tomorrow then we'll be doing the Unit 2 retake. Monday we'll be graphing polynomials. Okay, so beyond just cubics, we'll be graphing polynomials. Okay, Tuesday will be review, and then Wednesday will be test. So let's see here. So test Unit 3. What's that? 18. 7 weeks later, so 18. Okay, test Unit 18. All right. I will really try to get you guys the review for the test by Friday, like tomorrow maybe, so you can start looking at it over the weekend if you want to, and start to see what's all expected and stuff. Understanding that we won't have gotten through everything until Monday, but anyway, I'm gonna try and do that, okay, for you guys. All right. Anyway. So let's get into what we're going to do here. So, all right. Then we'll just start off with an example. Okay. We'll find the zeros of p of x equal to x to the third plus 8x squared plus 21x plus 18. Okay. So kind of a review of what we did yesterday, right? All right. So we'll kind of go through our things here. So we want factors of 18, and we're going to put those over factors of our lead coefficient there, which is 1. All right, so factors of 18, factors of the 1 there. Okay. So what are the factors of 18? 1, 2, 3, 6, 9, and 18. Yeah, okay? All over plus or minus 1, right? So our list of the possible zeros. So we're going to have 1, 2, plus or minus 1, 2, 3, 6, 9, and 18, right? Lots of possibilities to guess there. All right. So let's guess one of our answers, right? So I'm going to guess 6. Okay, Mr. Wade, you told us to start with the small numbers and make our way up. You're not doing that. I know. I'm not doing it on purpose. Okay, just want to illustrate something. All right. So we're going to put 6 in the box, and then what goes across the top here? 1, 8,
2.
not 2, 21. Oh, you can't see it, sorry. Yeah, it's 21. It's my handwriting. 21. And then 18, right? Okay. Leave a line of space, right? Put a little bar there. Okay. Remember, for synthetic division, right, we add vertically, and then whatever answer is we get down here, we multiply with a 6 and put it in the next kind of column over, right? So for this one, there's no number for us to add with the 1, so we drop that 1 down. It'll be 1 times 6, which is 6. 6 plus 8 is 14. Okay. 14 times 6 is going to be 84. Check the work here. Yep, 84. Okay. 21 plus 84 is going to be 105. And then 105 times 6 will be 630. And then we get 648. So, oh. Okay. So, is 6 one of our zeros? No, decidedly not, right? Very much not, because we get that positive 648. So, here's a strategy for you, right? 6 didn't work, right? I dropped the 1 down, times 6 made it 6, added that up, made it bigger. 14 times 6 was 84, added that up, 105, makes it bigger, so on and so forth, right? So, if 6 didn't work, is positive 9 or positive 18 going to work? No, because we're going to be multiplying, instead of multiplying by 6, we'll be multiplying by 9 or by 18, and these numbers are going to get bigger and bigger, and there's no way they'll cancel out, because these are all positive here, right? We're just going to keep adding to be bigger numbers. Now, some of these were negative, right? They might like reduce in size, and that could change it up. But since these are all positive, right, these are just going to get bigger and bigger and bigger as you go, and so in fact, 6 is not going to work here. Right? And nothing bigger than 6 will work. All right. Will any positive number work here in this case? No, right? If you even think about positive 1, right, it's going to be 1 times 1, 1, and then this is going to add up and get bigger, and this is going to add up and get bigger, and this is going to add up and get bigger, right? There's no way this is going to cancel out to make 0 if you always use positive numbers. So a strategy you can use, right, is when all of your numbers are positive, when all of your coefficients are positive, okay, a positive 0 is not going to make sense. It's just going to keep making things bigger and bigger and bigger. Okay? And let me just say one little caveat, one little, just side note here. If any of these strategies to you are like, I don't get that, then don't worry about it. You need to use any of these strategies. I will try to make sure these problems are in such a way that you don't really need any of the strategies. But feel free to use the strategies to help you if you want. So I only throw these strategies out just to help you. They're not something I'm going to test you on or make you know. Okay? You can just guess and check. That's fine. But the strategies will help you do better. All right. So no positive numbers would make sense here. So yeah, forget that. All right. So then let's guess a negative number then. All right. And let's just, for the sake of this, let's go ahead and just guess negative 2. Okay, and I'll put the same numbers across the top, right? 1, 8, 21, 18. And now we'll do the same thing. Okay. Is negative 2 a 0 of its polynomial? Is negative 2 a 0 of this polynomial? Yes, right? It gives us a remainder of 0. At this point, we could continue factoring. You could continue guessing and checking. In fact, if you look here, our constant term changed. Okay? It's now 9. So, for example, you would not need to worry about the negative 18 as a possibility because we only need factors of 9. And you could actually then throw out the negative 6 as well, okay, and the negative 2 as well, right? Because at this point, we're only looking for factors of 9 over factors of 1. So you'd be able to eliminate some of these other zeros because now we reduce from an 18 to a 9. So that changes your list of possible zeros if you were to continue guessing and checking. But we don't need to continue guessing and checking because we now have a quadratic, right? It's 1x squared plus 6x plus 9. And we know how to factor this, right? We need two numbers that multiply to make 9 but add to make 6. So what's that? What are those two numbers going to be? 3 and 3. You got it. Yeah, 3 and 3. Okay. So long story short, p of x, okay, which is, which started in standard form as x cubed plus 8x squared plus 21x plus 18, is really in factored form x. If negative 2 worked, then what's the factor? X plus 2. So remember that this is the 0 that you put in the box. The factor then would be the opposite, right? What when you solve it gives you a negative 2, x plus 2 when you solve it gives you that negative 2. And of course the x plus 3. And I'll go ahead and write x plus 3 squared. Okay? Okay. We have a something that came up again in the homework too, where a 0 worked more than once, right? That negative 3 kind of happens twice. Okay? So negative 3 happens twice. When your 0 happens, well, the number of times your 0 occurs or works, okay, that's referred to as the multiplicity. Okay. The number of times that a factor slash 0, right? Because we can kind of refer to it for both of them. Okay. So the multiplicity is just the number of times that a factor slash 0 occurs in a given polynomial. Okay. So what is the multiplicity of our x plus 3 factor here? Multiplicity is 2. 2, okay? Occurs twice, right? So, or you could say the multiplicity of the 0 of negative 3 is 2 as well, right? So either the factor has a multiplicity of 2 or the 0 of negative 3 would also have multiplicity of 2. What's multiplicity of this 0? 1. We typically don't list if it's multiplicity 1 because you would assume because it's a 0 by nature its multiplicity will be 1. We only really concern ourselves when the multiplicity is more than 1, when it occurs more than once, right? Simply by listing that it is a 0, you're guaranteed a multiplicity of 1, right? Because it exists as a 0 in the first place. It's only when we have it occur more than once that then we have a higher multiplicity. Okay? Question on any of that? All good? Okay, question.
So if you put a different number in first and it works and you end up with the same thing, is it okay?
Yeah.
Because you could put negative 3 in and then
Absolutely.
factor it out the rest of it. Okay.
Mm-hmm. Yep. So your work will be the path will be slightly different, but the final answer, right, will still be the same. Yeah. And that's what's going to happen is different people will guess different numbers, but your ultimate goal is all still the same. You want to get down to a quadratic and then factor that quadratic and then rewrite it as a product of its factors and stuff. Okay. So let's see. All right. So let's have you guys try one. So let's have you solve. Solve x to the fourth minus 81 equals 0. Okay. Include any multiplicities greater than 1. Okay. Include any multiplicities greater than 1. Okay. Ooh, and give me all of your answers. Well, okay. Give me both real and imaginary solutions for this too, please. Okay. Give me both the real and imaginary solutions for this too, please. You're welcome to try to use your factor stuff, like factors of p, factors of q, but this one also factors. So I would encourage you to factor, use factoring here. Okay. This one does factor, so I would encourage you to factor because it factors. Bless you, bless you, bless you, bless you. So, there are your answers up there on the board. Okay. Question.
Can I go to the bathroom?
Yes. Mm-hmm. Okay. How many zeros are there? Yeah, there's actually 4, right? Because that plus or minus counts as 2 different ones, right? A positive 3i and negative 3i. So there are 4 zeros here. What was the degree of our original polynomial? 4. Right? 4 zeros, degree 4. Okay? 2 real in this case, 2 imaginary, right? But the total number was 4 zeros. Okay? And so there's your answer. Again, when it comes to solving these polynomials, right? You have a big bag of tricks now, right? You can, if it's, we have GCF first, right? Factoring by GCF. And again, why we factor when we're solving these? Because we're trying to create products that are equal to 0. When you have a product of 2 things equal to 0, that means you can set the individual parts of that product equal to that 0 and then continue solving from there. Okay, so that's the whole purpose of factoring in these situations, right? It doesn't say factor, but that's the idea. You want to create a product, okay? A multiplication. So, use all strategies at your disposal. Difference of squares, difference of cubes, sum of cubes, factor by grouping, factor like it's a quadratic, okay? GCF, like I said. If all that factoring stuff doesn't work, then you should fall back on the not the P's and Q's, but like the factors of the factors of the constant term over factors of the lead coefficient, that rational roots test that we did. And then you have to guess and check your zeros from there, okay? So anyway, yeah. But there it is. Okay, there it is, right there. All right, and then you set each factor equal to 0, and you solve individually there. Okay? You could have used quadratic formula here if you wanted to, but this one we actually could have I just solved using square roots because we can subtract 9 over square root of 6. Okay? So, this idea of having the number of zeros be equal to the degree is something called the fundamental theorem of algebra. Okay? So this is a big important theorem, although it doesn't really seem that impressive. Oh, sorry, thank you. Okay, and so I'm going to write it out just because it's a fundamental theorem. It's an important theorem, but it's not really that surprising. But it's very important. Every polynomial, function of degree n greater than or equal to 1 has at least 1 0. And I'll put in parentheses complex. Okay, so 1 complex 0. Okay? Not that impressive, right? Every polynomial function of degree n greater than or equal to 1 has at least 1 0. Not that impressive, right? But then there's a corollary to that, so there's a little supplement here too. Every polynomial function of degree n greater than or equal to 1 has exactly n zeros, including multiplicities. Okay. So if you have a 5th degree polynomial, you should have 5 zeros. Some of those zeros might repeat, right? So you could have 1 0 that has a multiplicity of 4, and then another single 0 kind of thing, okay? But including multiplicities, every polynomial function that has a degree greater than or equal to 1 will have that many zeros to it, okay? That many zeros. But again, the multiplicities also are counted there. Alrighty. I have one more thing I got to show you here that I forgot about. So we are, running short on time. I'm sorry for that. Okay. Before I get into the next thing, is there anyone that knows for sure they want to come in for set? And I'll just put you guys in right now because I know we got the thing tomorrow too. So Sienna, yes. Okay. I'll just do it real quick here. Anybody else for set? Yes. Megan, Kaylee, gotcha. Michael, and yeah. Okay. Yes. Maya got you. Okay, Brooke got you. And then Ash got you. Anybody else? All right. Let me put those folks in here real quick, and then we'll talk about this last thing here too. The last thing I want to talk about is writing a polynomial from its zeros. We've kind of been doing that, okay? But I want to kind of formally do it here too. Okay? So, so I'll just do an example here. Write the polynomial function of least degree, and I'll talk about why we're doing least degree, why we have to say that, and leading coefficient of 1 that has the given zeros. Okay. so let's talk about some of those zeros here. And I'll just pick an example here. So like for this first situation, let's just do it like super straightforward here. And let's just do like, I don't know, zeros at like 2 and 1, we'll say. Okay, so 2 and 1. Okay, so if we have zeros at 2 and 1, right, what kind of factors yield these zeros? So if I get a 0 at 2, then what factor, what thing in parentheses here, right, is going to give me that? Well, think about this, right? X equals 2, when we solve these equations, we end up at x equals 2, and that's how we get our answer, or x equals 1 here, right? But if we work backwards, right, where did this x equal 2 come from? How did we get to this in the first place? What would have been our next step right prior to this? X minus 2 is equal to what? 0, right? And there's a 0, right? There's the factor that yields x equals 2, right? What about here for x equals 1? It would be, yeah, x minus 1 is equal to 0. Okay? So the original factors that give us 2 and 1 as zeros would be x minus 2 and x minus 1. Just like that. Okay, you multiply those two things together, it's that equal to 0, right? Okay. So it's kind of like working backwards here. All right? Now, we should also be able to multiply this out, right? And then get the actual like function in standard form. So in other words, you should be able to say, okay, well, if that's the, those are the factors, then, x squared, let's see, minus 3x plus 2 equals 0. This polynomial right there, okay, would yield those zeros. Okay. And so there is our polynomial. Does it have a lead coefficient of 1? It does, right? So that's good too, because that was part of our stipulations. Okay, and it's the smallest degree that we could possibly have it be. And I'll talk about that here, how we know that. Because remember with the multiplicity stuff we talked about, okay, with multiplicity, right, I could do something like this. I'll put it over here maybe. Right? Would not these also give us 2 and 1 as zeros? Right? They would, right? This 2 would make a 0 here, 1 would make a 0 here, so 2 and 1 are still zeros. But here the multiplicity is 3, right? Imagine multiplying this out. It would not be the smallest degree because you'd have, x minus 2 times x minus 2 times x minus 2, and then an x minus 1. It would be, a, fourth degree polynomial there. Okay? You don't have to worry about that. Right? Make it small as possible, as small as you need. So we just need an x minus 2 and an x minus 1, and that creates the smallest degree polynomial. Okay. Other options here, right? We could have written like 2x minus 4, and I don't know, 3x minus 3 here if we wanted to. Wouldn't this still give me 2 when I set it equal to 0 and solve? Right? Add the 4 over, divide by 2. Or wouldn't this still give me 1 if I add the 3 over and divide by 3? Right? But then our lead coefficient would be, 3 times 2 would be 6. Right? And we want a lead coefficient of 1. So again, the idea here is we're not trying to make these more complex than we need to. We're trying to keep it as simple as we can. And so we just go with the very simplest factor, okay, that would yield the zeros we're looking for, and then multiply them out potentially too. Okay? But let's talk about some other situations. So actually, questions on that before I move on? Does that make sense? We're just building the polynomial here. So then what about like what if we had these kind of zeros? 5 and 3 plus 2 root 7. Okay. So 5 factor, the factor for 5 we can make very easily, right? What is the factor for 5? It's going to be x minus 5, right? Because that's what it's going to be, right? Okay, right? So just x minus 5. But this factor, how are we going to do this? And first of all, by the way, second of all, I should really say, if we have this as a 0, what other 0 must we have? If we have 3 plus 2 root 7, what other 0 must be included too?
Minus 2 root 7.
3 minus 2 root 7. Okay? You have to have its conjugate as well. So, what do we do here? Well, we could follow the same idea that we did right here, where if you have a positive 5, x minus 5. So for this one, we could do x minus 3 plus 2 root 7 and x minus 3 minus 2 root 7. Okay, and so you could say your polynomial was x minus 5 times x minus 3 plus 2 root 7 times x minus 3 minus 2 root 7. Okay? It's not very elegant, right? It's kind of like awful looking. You never really see a polynomial like that. And imagine trying to multiply that out. Right? Imagine trying to multiply that out. You'd want to distribute the minus sign here to both these terms, distribute the minus sign to both these terms, and then you have a trinomial here times a trinomial here. Get that answer, and then you multiply the x minus 5 times the answer of that. That's one way to do it. Okay? But let me show you an alternative to help you handle these like yucky, irrational, zeros there. So back to this idea that I talked about before where we work backwards from the zeros we had to then make our factors. Let's do that here for this too. So we'll say x is 3 plus or minus 2 square root of 7. Okay? So just like that. Okay. Right? Those are our zeros. And I did both the positive and negative version here because typically we do end up with them at the same spot. Okay? Let's imagine undoing this then. What could we do here to start kind of like undoing this answer that we've got here? What would be like the first step to kind of like undo this, to work backwards? What do you guys think? What should we do to both sides here? Subtract 3 from both sides. Yep, we'll subtract the 3 from both sides. So we have x minus 3 equals plus or minus 2 square root of 7. Okay. And then we want to get rid of this 2. Okay. So to get rid of the 2 times root 7, what should we do? We're going to divide both sides by 2, okay? So we'll end up with like 1/2 x minus 3 halves there, right? I'll just 1/2 x minus 3 halves. And then the plus or minus will still stay in front, like that. Okay. Now, how do we get rid of a square root?
Square.
Yeah, square. So we can square both sides here. Now, when I square a positive root 7, what does that become? Positive square root of 7 squared, what does that become? 7, just 7, right? And if I square a negative square root of 7, well, what's a negative times a negative? Positive again. So this just becomes 7. So that's how we deal with that plus or minus. When you square the plus or minus square root there, it just goes away. Plus or minus goes away because when you square a positive number, bless you, it becomes positive, and a negative number squared becomes positive as well. And so we still have, I'm not going to multiply this out, I'm just going to leave it like this for right now. Bless you. Okay? And then the last step we need to take to make this thing a 0, subtract the 7 over. Okay? And so there is our factor right there. So instead of writing these 2, okay, you can just write this 1 right here. And so it'll be x minus 5 times this. Okay, like that. Is that better? I know you guys don't like practice very much, but I don't know. It would be easier to multiply out, right? It's much easier to square this and then subtract the 7. You'll have a trinomial times your binomial there. But that would be your answer. Okay, I will try to keep that. Anyway, yeah, Max.
Could you take the 2? I'm thinking this. You could take the 3, subtract it, and then could you turn the 2 back into square root of 4, and then back into the square root of 28?
Yep, you could do that. Absolutely, yeah. So Max was saying bring that 2 inside the square root, so it would become a 4 when you bring it inside times 7 to make it a 28, and then you wouldn't have those fractions there. So that's an that's an option too. Yeah, especially because then that would create a situation where we're not going to have a lead coefficient of 1 there. But anyway, yeah, we'll talk about that. All right. So anyway, I'll assign you guys. I'll put you guys homework on Schoology. So please check Schoology for the homework. Okay. I'll also show you one tomorrow with imaginary numbers, or not tomorrow, Monday, I guess, with imaginary numbers because I didn't do one of those. All right. All right. I will try to avoid these fraction ones for you though. So. Oh yes, the test. Thank you.